I don't think everyone's gonna make it today. We'll see.
Why do you say that?
Because good Gonzalo's online and I know Yasmina's at the embassy. What?
Where'd you say embassy?
Embassy, yeah, in LA. She messaged me.
Sure.
No, Yasmina. Gonzalo, you can see the shared screen here?
Yeah, I can see it. It's all good.
All good. Well, that's 5. You're getting close. She said 5. He said 8.
How
So
many
it's-
need to be here before you cancel class?
I never cancel class. Why would I cancel class? So you're paying for your education. I'm not paying anything. I get paid whether or not you show up.
You know, I always forget.
Yeah. How's everyone doing? How's their weekend?
Good.
Is there anything fun?
I have a photo of a girlfriend. She said yes.
That's very fun. Now no one can top that. You know anything fun? Did you get proposed to? No. Anyone in the back? No. Me neither. I didn't get proposed to. Okay, bummer. So we're getting close. There's 2 weeks. Don't throw
So
up
it's
in your
time
mouth.
to panic.
Yeah, this is the panic time, right? So one of the things about integration methods, and I was having this conversation with a colleague over the weekend. It's important to understand how we do these integrals in the context of some more advanced types of computational analysis. But if we get through today and you're saying to yourself, man, I really wish that we had another catch-up day, either Wednesday or next Monday, that would be perfectly okay with me. Because some of the higher order integration or Gaussian quadrature, for example, it's good to know, but Wolfram does a very good job, and there's plenty of really good code out there on integration. So understanding sort of the theoretical basis for it is more important to me than you being able to create things that do these integrals for you. And in particular, I think it's much more important for me to see that you are able to do all of the work that we've done so far. The easiest way to fail this class is to just not have your homework done, right? And that is easy for me too, because then I just look and I say, oh, nothing was done here. In particular, if you decide that, I'm going to do all of the homeworks on ChatGPT and I'm just going to turn in what it says, and that will not have comments in it. It will not demonstrate your understanding, because we talked about at the very beginning of the class, you need to be able to demonstrate how you knew your code worked and why it worked. So if it's missing that, right, that'll give you like a 70%. So let's say you turn in all your homeworks ChatGPT style. Sure, 70% seems fine, but then I have to take into account presentation, coming to class, etc. Right? So I don't want to fail people. I want everyone to succeed, because my goal as an educator is to make sure you're doing well, not to like be some gatekeeper who only lets specific people in and like blocks other people from their goals in life. So I would love for you to give me feedback probably by the end of today as to whether or not you want to, we could take either this class here, this Wednesday class, and we can just turn it into sort of an overview of the choosing integration. I think you need this one here, 5.7, but you don't necessarily need all of these 3 if we don't really want to see it. This is really fun. I think that this is valuable, but might be less pressing for some folks if they're sort of stuck on their problem, for example. So if you want, we could make this a catch-up day, or we could make this a catch-up day, or we could do all 3. I don't care. But you will have to submit your code relatively soon. And I hope that your code is 80% done or 50% done at this point. You have code? Okay. That's the starting point. At this point, you have code that does something, right? Okay. Because you also need to start thinking about your presentation. Okay. Finally, and this is the most important thing to me. Well, not to me, but let's go to the other course. Yeah, you don't need to do computational analysis. I promise that. Okay, so this is the only thing that I need to point out. Yeah, zeros of 11. I need one of you. Ideally, all four of you after Daniel's presentation, all four of you will do it, and I'll leave the room for like 5 or 10 minutes. But ideally, if we can get this up to 50%, the department will be happy with me. We're trying something new out, right? And so this is the first time that I've taught it ungraded, with not giving strict deadlines and not giving points off for missing stuff. So I'd love honest feedback. Do you feel like that helped you succeed? Do you feel like that with your learning style made it easier to slack off, prioritize other classes? Do you feel like you got as much as you wanted out of this class, etc.? Does that make sense? And that way, next time I teach it, I can do it better. Okay. Questions, comments, concern before we get started today? All right. Let us do one of these is correct. One of these is a homework from a different class. Okay, let's talk about errors.
So just a quick summary. I'm sure you'll get more into detail with the equations down there below. But what we're learning in this section, there's talking about how the trapezoidal rule and the Simpson rule, they're both good at what they do, which is give us approximations. But we know that there's an error to that because we're approximating the area under the curve using like linear or quadratic formulas. So what we're doing in this situation is we're learning that the trapezoidal rule and the Simpson rule, they're good up to the first and second derivatives. I believe it's in the Simpson rule that the second order or the second term that we get when we do the Taylor series from it is the actual error that we get. So the first term is the estimate of the approximation, and then the second term gives us the error, so we could actually account for it. One thing that they do notice at the end of all these equations, if you want to go below, is that I believe the odd terms cancel out evenly. So we're left with equation 20, which is the error that we would normally get for, I believe, second order derivative that we get when we have an equation with like a second order derivative from it. And then it pretty much goes on to say that we're going to learn this new formula called the Euler-Maclaurin formula. And that one, it gives us a higher estimation. So we could actually go to I believe, third derivatives for it. And they say anything above the fourth, which is over there where you can see the O. Those are negligible. So you don't really have to account for those terms. And that's why it cancels out at the end.
Yeah, so let's pause there for a second. Let's remember what all these words mean just because it's Monday. What does O mean here? Not Daniel. Terms of what? Yeah, what does the O stand for?
That's for the rest of the terms in the students.
And what does the O stand for? Order. The O is for order. So what this says is this is all terms of order h to the 4 and higher. Okay. Now, why can we ignore terms of greater powers of h? Usually powers of h mean bigger numbers. Sure, but what about h makes it okay to ignore large powers of h? This is the same type of rule that we applied for derivatives too. Something about h itself allows us to take larger and larger powers of it, and then it's ignorable. It has to be less than 1 and greater than 0, right? So it's between 0 and 1. And as long as it's between 0 and 1, then every time we square it or take the cube of it, it gets smaller. So larger powers of h are more ignorable, right? Okay. So this is why we collect the terms like this. Here's that h squared. This is your second biggest term. This is your h. This is your biggest term, right? And when we say something like to leading order in h, that would be this one. Cool. That okay?
Yeah, and then there's no third H because that one cancels out.
Yeah. Good. Okay.
So there we get I want to say from here on out, they say that the Simpson rule and the trapezoidal rule, they're pretty much interchangeable with the degrees of accuracies you're going to get and errors you're going to get. They do say that you should really look at the formula you get, because for most formulas you could use either one, but obviously like it has like a higher derivatives on it, then you would either go with the Simpson rule or do the Euler.
Yeah, I mean, I think for this section in particular, one of the things that we're going to focus on is this this fight between the two different types of error. One is which we're approximating the area under the curve. And then when we take too many small numbers and we try to add them, we get what kind of error? Numerical error, right? Because the numbers themselves don't have infinite digits of precision. A numerical error can build up.
Yeah,
Right.
that's what they mentioned in the bottom. The constant is around 10 to the negative 16th power. That's the
Yeah.
error constant. That's like naturally in the system.
Right. Good. I think in particular, we shouldn't necessarily go into the derivation of these ones here, but let's see, where was the problem? I want to say the practical estimation. Yeah, here we go. Did this section make sense to you?
I haven't done an example for it because the example for this week is the 5.4,
Mm-hmm.
and that one you could still get away with using.
Simpsons?
Pretty much, yeah.
Okay.
I think I use a trap. So.
Yeah. Yeah, so I think let's just talk probably about choosing the right number of steps. The way that these integral, we take better and better versions of the integral. So for example, if I have the number of steps, if I have the size of the step, I get twice as many steps. So let's say my h goes from 1/2 to 1/4, right? To cover the same distance, I would need to double it. There is a relationship between what the new integral was and what the old integral was. And we use that for a technique called Romberg integration, where we take successive approximations of the integral. But I think that's outside of the scope of what we want to focus on here, for the same reasons we talked about at the beginning of class. But let's talk about using the right number of steps, thinking about these two issues, one of which is that we need to approximate the integral well, while also not taking infinite number of steps because you run into numerical error, right? You want to talk about this one here?
Okay.
You didn't cover it? Okay. That is basically the whole of the problem. Look at, this is some region. And so this is the size of the step H in between here. And if we double it, we get more points in between, right? The edges stay the same. They still get the same weight, but the ones in the middle get more of a weight. Okay. This is an error approximation. So what this says here is eta I, this would be like your word accuracy or error on the integral. And what this would do is this would say, let's take some number of steps, say 100 steps, and we're going to double it. We're always going to do twice as many in the next one. So if we started with a step of size half, then our step becomes a quarter, and then an eighth, and then a 16th, and so on and so forth. And at each step, at each time that we calculate the integral, we take the difference between the integral and the one that we just calculated, the new one and the old one, divide by 3 and see if it's less than the error. And by the time that we get the answer is not changing by enough, by the amount in the error, then we can stop. Does that make sense? It's kind of the same way we did it before. So let's see. Let's go to, this is the entire process here. Choose an initial number of steps and decide on some target accuracy. Calculate the first approximation using your initial H, right? Then double the number of steps to create an improvement and calculate that error. If you find the total magnitude is less than the target, stop. Otherwise, do it again, right? So it's a very sort of a straightforward way of assessing how many steps you need in order to take the integral. So you don't want to start with, 10 to the minus 5 as your H. Start with something that's less than 1, but more than 0. Make sense? Okay. Where's the example? Oh, it's inside of, is the example in, yeah, it's in 5.4, huh?
Yeah, it's the example. The exercise 5.4 is before 5.26.
Right. Oh, there is no example for this section. Interesting. Okay, that's silly. All right, let's look at 5.4 for today. No, this is not the problem I want to do today. Let's switch. Let's do okay. Let's do 5.6 here. And I'm going to put 5.4 as your homework here. Does that make sense? Did you already start it? No. You're not talking about that. Okay. That's 8. It's pretty good. It's pretty good. Okay. So we're going to do 5.6 today. And this is write a program or modify an earlier one to calculate the value of this integral using the trapezoidal rule with 20 slices. But this time have the program also print an estimate of the error on the result using this method right here. Right? Okay. To do this, you will need to evaluate the integral twice, once with n equals 10 slices and then with n equals 20 slices. How does the error calculated in this manner compare with the direct computation of the error as the difference between your value of the integral and the true value of 4.4? Why don't the two agree completely? So this is a very like pinky brain one, right? But it will need us to create a program. So if you created the program to do trapezoidal already and that works, but your Simpsons does not, do the Simpsons one, right? If they both work, then you can choose whichever one you're more comfortable with. Okay. I'm going to just leave this here for a second. There's 8 of you. So I'm going to walk out of the room for like 10 minutes and you're going to do SOTIs in class. And I'm going to stop the recording. What? No, I wasn't in here. I'm going to leave. Okay. And then if someone, no. I'll bring, no, I won't even, I can't bring snacks. I can't do anything to influence you. So I just leave and I don't say anything about it. The only thing that matters to me is that you fill it out. And that gives us feedback for the next time that I teach. Okay. So let me pause this here and I'll just like come to the window and like knock on it. And if you're still working on it, just go away, Chris Money.